Welcome to AI Paperslop. Today we are looking at From Foundation to Application, Improving VLA Models in Practice by researchers at Ant Group and Robiant.
Yeah, this is a big one.
It really is. And for the ML engineers and robotics researchers listening, here is the absolute bottom line right up front. The team behind Lingbot VLA 2.0 has systematically tackled that massive, super frustrating sim-to-real gap that just plagues vision language action models.
Right, the gap that breaks everyone's models in the real world.
Exactly. And they didn't just, blindly scale parameters and hope for the best. They engineered their way out of three critical bottlenecks. First, curating 60,000 hours of multi-embodiment data. Second, unifying control into a single 55-dimensional action space.
That's huge.
Oh, it handles everything from dexterous hands to mobile bases. And third, they forced the model to predict the immediate future through this really novel dual-query distillation process.
So the mission for this deep dive into the sources today is to basically unpack the underlying mechanics of that exact pipeline. We're going to look under the hood at their architecture choices, specifically this highly efficient, loss-free mixture of expert setup, and break down a series of ablation studies on action spaces that will honestly fundamentally change how you represent robot movement in your own models.
Yeah, I totally agree. So let's just start with the data engine, because throwing 90,000 hours of raw multi-embodiment video at a transformer is just a recipe for catastrophic failure.
Oh, absolutely. Total garbage in, garbage out scenario.
Right. I mean, you're trying to train a single brain to operate a bimanual robot, a mobile quadruped, and a single robotic arm simultaneously.
Yeah.
So the paper details this brutal filtering process to distill that initial 90,000 down to 50,000 hours of high-quality robotic data, plus 10,000 hours of egocentric human video.
Right, the head-mounted stuff.
Exactly. But they didn't just filter out, blurry video. They used kinematic thresholds. They calculate the third-order finite difference of the action signals, which is the jerk.
Yeah, jerk is so critical.
So why base a massive data culling operation on the third derivative of position? I mean, why is jerk the metric here?
Well, when you are dealing with physical hardware, high-frequency noise is just incredibly destructive.
Right.
If a model learns to replicate sudden, erratic changes in acceleration, which is literally what jerk measures, it will tear the gears out of a $100,000 robotic arm.
Oh, wow, yeah. Just shred the servos.
Exactly. So the researchers set these strict, embodiment-specific z-score thresholds for velocity, acceleration, and jerk. And any episode crossing those lines was just immediately discarded.
Just thrown right out.
Yep. But they also had to hunt down the exact opposite problem, which is dead data.
Right, the robot just doing nothing.
Right. If an episode consisted of static signals for more than 95% of the time, they dumped it. A model simply cannot learn dynamic manipulation if its training diet is just, a robot staring idly at a table.
That makes a ton of sense.
Yeah.
But then there's the human element, which I found fascinating. They included 10,000 hours of egocentric, head-mounted human video.
Yeah, human teleoperation data is super messy, though.
It is. And to avoid manually annotating all of that, they actually used a vision language model to pre-filter the pool.
Oh, smart.
Yeah, they're specifically looking for a minimum 20% valid hand-frame ratio, meaning if the camera wearer's hands weren't visible and actively manipulating something, the video was useless.
Toss it.
Exactly. They also tossed out unstable slam trajectories. But here is the major conceptual hurdle for me, right?
Okay.
If you combine robot data with human head-mounted camera data, the camera wearer's own body movements introduce massive noise.
Oh, absolutely.
Like, if I turn my head sharply to the left, my hands appear to sweep across the room to the right, even if they were perfectly still relative to the actual table.
Right, it's a relative motion illusion.
Yeah. So how do they prevent the model from learning that fake momentum?
So that specific failure mode ruins a lot of egocentric data sets.
I bet.
Their solution relies on this dynamic coordinate transformation trick, which is honestly brilliant. During the data processing phase, they store the human hand trajectories strictly in the world coordinate frame.
Okay, so the world frame is absolute.
Exactly, the world frame is absolute. But during training, when the network samples a specific video frame as its current observation, the pipeline dynamically transforms that future hand trajectory from the world frame into the current camera coordinate frame.
Oh, I see.
Yeah.
So the model is always learning to predict actions relative to its current visual perspective, effectively neutralizing the human operator's head movements.
Yeah.
So the world frame acts as an immutable storage ledger. But the training input is dynamically rendered to match the exact perspective of the lens at time t.
Right. It mathematically decouples the hand motion from the camera motion?
That is incredibly elegant. So, okay, we've mathematically scrubbed the jitter, the static noise, and the weird camera movement out of 60,000 hours of video.
Which is a huge win.
It is, but that creates a massive new headache, right? How does the neural net actually digest all this?
Yeah, the heterogeneous action space problem.
Exactly. You can't just feed mobile robot-based data into an array meant for a 14-joint bimanual arm.
Right. To solve this, they constructed a 55-dimensional unified action space. They basically mapped every heterogeneous embodiment control into one single compact canonical vector.
Yeah, and looking at the breakdown of those 55 dimensions, it's quite an engineering feat.
It's very dense.
Yeah, you have 14 dimensions allocated for the arm joints, 14 for the end effector pose, 2 for the gripper, 12 for the dexterous hand, 4 for the waist, 2 for the head, and 3 for the mobility base, with a few reserved. But what happens to the dimensions that a simpler robot just doesn't possess? Like a single arm robot doesn't have a mobile base.
They are simply padded.
Okay.
That padding guarantees the neural network has a consistent input and output structure, regardless of the hardware it's currently puppeteering.
That makes sense. And this brings us to the ablation studies on action targets, which is where things get genuinely counterintuitive.
Oh, the ablations are fascinating.
Yeah. Wait, hold on. The paper says they abandon absolute joint positions.
Yep.
My intuition as an engineer is that knowing exactly where the robot arm is in global space is mission critical. Why would throwing that away and only predicting the relative delta actually improve success rates?
It seems backwards, right?
It really does. But the paper says the average success rate jumped from 33.7% to 55.0% just by switching to relative joint actions.
So think of it like the difference between using hard-coded absolute memory addresses versus relative pointers in software architecture.
Okay, I'm with you.
If the network has to predict an absolute global joint configuration, it is trying to approximate a highly variant global map every single time it moves.
Right, which is a lot of variance.
Huge variance. By switching to relative targets, they compress the action scale. The standard deviation of relative joint actions is roughly a third of absolute actions.
Wow.
Yeah, you are basically converting a complex global regression into a localized centered motion regression. The network just calculates the offset.
Oh, that makes so much sense.
Uh-huh.
And if you are an ML engineer listening to this and currently using min-max normalization for your robot telemetry out of habit, their next ablation is a massive wake-up call.
Oh yeah, ditch the min-max.
Seriously, they tested mean normalization against min-max and a quantile normalization spanning Q01 to Q99. And mean-stid was the clear winner.
By a lot.
Yeah. Because from what I understand, min-max compresses the entire range of values into a strict boundary, usually -1 to 1, which just absolutely destroys the resolution of your data.
Exactly. Robotic manipulation data has a severe long-tail distribution. The vast majority of the time, a relative action is a microscopic correction hovering right around 0. But occasionally, the robot executes a massive sweeping movement.
Like swinging its arm across the table.
Exactly. So min-max normalization forces all of those subtle, high-density, small corrections into a tiny fraction of your available floating point resolution, just to make room for the rare extreme value.
Which means you lose the precision.
You completely lose it. Min-CTI preserves the dynamic range. It allows the long-tailed, large corrective motions to exist as values outside the standard range without crushing the resolution needed for precise sub-millimeter movements.
That perfectly explains their loss function ablation too, because they found that L2 loss beat L1 loss.
Yeah, which is unusual.
It is. Usually L1 is preferred for heavy-tail distributions because it doesn't over-penalize outliers. But because they are predicting relative actions, the vast majority of the targets are those tiny corrections clustering tightly around 0. So L2 fits that high-density, small variance region much better than L1, effectively encouraging the model to master precise micro-adjustments.
That is the exact mathematical mechanism at play there.
But the ablation that really made me pause was the comparison between the end effector space, the EEF, against the joint action space.
Ah, the classic Cartesian space versus configuration space debate.
Exactly. It's like asking a human to navigate by thinking about the exact angle of their elbow and shoulder versus just thinking about the XYZ coordinates of their fingertips.
Right.
And the results were completely split depending on the physical task.
Yeah, this part is crazy.
Squeezing a ketchup bottle worked wildly better in EEF space, 81.7% success versus 41.7% for joint space.
Huge difference.
But scanning a barcode worked much better in joint space, 58.7% versus 24.0%. Why is there this massive split?
It really comes down to two intersecting factors: the physics of the task and distribution alignment. So, squeezing ketchup is a contact-rich endpoint task. It requires high Cartesian precision at the tooltip. The model needs to reason about the exact spatial coordinates of the bottle. Fingertip-level awareness, which is the EEF space, just dominates there.
Okay, but barcode scanning isn't just about reaching a point in space.
Exactly. Barcode scanning is about orientation, posture, and reachability constraints relative to the object.
Oh, right.
The arm has to contort into a very specific posture to face the scanner toward the barcode without colliding with the table or itself.
The actual angles matter more.
Yes. Tasks dependent on specific arm configurations demand joint-level awareness. And to actually quantify this, the researchers mapped the task-specific action distributions against the pooled overall pre-training distribution.
And what did they find?
For the barcode task, the joint actions were mathematically much closer to the overall pre-training distribution than the EEF actions.
So the network was naturally more comfortable outputting those joint configurations because they looked like its training data. But wait, for the scooping rice task, the EEF outperformed joint despite having a larger distribution gap.
Which proves you cannot simply default to whichever action space looks more like your pre-training data.
That's fascinating.
Yeah, the intrinsic geometric requirements of the physical task, like the Cartesian motion regularity required to scoop a bowl of rice without spilling it, can outweigh pure statistical alignment. You have to intimately understand the kinematics of your deployment environment.
Wow. Okay, so we have this optimized 55-dimensional multi-embodiment vector, but computing that across millions of parameters without blowing up your latency or your cloud budget requires a massive architectural shift.
It does.
They replaced the standard dense feed-forward network in the Action Expert with sparse mixture of experts layers.
Yeah, specifically, they used SweetLU MLPs for these experts.
CGY.
SweetLU activations help maintain a smooth gradient flow, which is absolutely critical in sparse routing where you are constantly activating and deactivating different pathways. It basically prevents neurons from dying during training.
Yeah.
And they structured this MOE with one shared expert and multiple routed experts.
What's the difference?
The shared expert acts as a permanent repository for universal priors. So like the fundamental physics of gravity, friction, and momentum that apply equally to all robots.
Oh, that makes sense.
Yeah, and the routed experts are activated selectively to handle highly specialized tasks or unique embodiment dynamics.
Got it. And the routing mechanism is where they pulled a brilliant trick inspired by DeepSeek v3.
Yeah, this is so clever.
They completely abandoned the standard softmax function for load balancing, and they swapped it for a sigmoid activated function for the router logits.
Yes.
Because, like, softmax forces your experts into a zero-sum deathmatch. Because all the probabilities have to sum to 1. If one expert claims a token, it actively suppresses all the others.
Exactly.
But sigmoid acts more like a collaborative board of directors. Multiple experts can look at a token and independently say, hey, I have high confidence on this.
Right. And in cross-embodiment pre-training, representations are deeply entangled.
What do you mean?
Well, a single action token representing a robot grasping a mug contains data about the physics of friction, the geometry of the cylinder, and the kinematic constraints of that specific robotic arm.
Oh, so it's a lot of different concepts at once.
Exactly. The model absolutely requires overlapping expert activations to process that multidimensional reality. Softmax creates an artificial bottleneck there.
But if you sigmoid and let everyone volunteer, how do you prevent all the tokens from crowding into one popular expert, leaving the rest of the network idle?
Yeah, the load balancing problem.
Normally, you'd add an auxiliary loss penalty to the training objective, punishing the model if it doesn't distribute the workload evenly. But this paper touts an auxiliary loss-free mechanism. If you don't penalize the network, how does it balance the load?
Through a highly effective bias adjustment mechanism that basically decouples expert assignment from expert routing weights.
Okay, how does that work?
The system maintains a running tally of token distribution. If an expert is underutilized over a batch, the system quietly adds a writing correction bias to its pre-Sigmoid score.
And if it's overutilized.
If an expert is hogging tokens, it subtracts from that bias.
So they are secretly putting a thumb on the scale behind the scenes to force the traffic into different lanes.
They are, but, and this is the absolute genius of the design, the actual routing weights used to multiply the outputs during the forward pass are computed from the original unbiased affinities.
Oh, wow.
Yeah. The bias only dictates who gets chosen, not the magnitude of their contribution.
That's brilliant.
It achieves perfect hardware load balancing without injecting an artificial penalty into the primary loss function. Any auxiliary loss inherently degrades the primary objective, which is learning precise motor control.
Makes total sense.
And their matched parameter scaling experiments demonstrated this clearly. This loss-free MOE setup achieves lower training loss and lower validation error than a dense model utilizing the exact same number of active parameters.
It is a masterclass in allocating model capacity. So, okay, now we have a clean data pipeline, a unified control space, and an incredibly efficient architecture. But a robot operating in a dynamic physical environment can't just react frame by frame.
No, it would be way too slow.
Right, it has to anticipate the physics of the immediate future. And this brings us to their dual query distillation process.
Yeah, because a purely reactive vision language action model will constantly lag behind the real world, leading to jerky, corrective behaviors.
Nobody wants a jittery robot.
No. So Lingbot VLA 2.0 solves this by injecting predictive dynamics directly into the transformer architecture. They append two learnable queries to the visual and textual tokens. Qt, representing the current state, and Qt plus T representing the future state, where T is the action chunk size.
Meaning the model is actively trying to predict the exact state of the world after its current sequence of actions is fully executed. And to teach the model how to do that, they use two separate teacher models to distill knowledge into these queries, Lingbot Depth and Dino Video. So how do these two teachers actually inject that knowledge?
Well, Lingbot Depth is trained to provide explicit geometric and spatial priors. It teaches the network the 3D structure of the environment.
Okay.
While Dino Video, which is a causal video model built on the Dino V3 architecture, provides temporally grounded, motion-aware visual features. It basically understands the flow of time and object permanence.
Ah. So Lingbot Depth is teaching the robot where the physical edge of the table is located right now.
Right.
But Dino Video is teaching the robot the causality of how a coffee cup will accelerate toward the floor if it gets pushed past that edge.
Precisely. And by forcing the future query, Qt plus T, to predict the future latent states of these two specific representations, the VLA model inherently learns the physical consequences of its own actions.
Oh.
It bridges the gap between spatial awareness and temporal progression. The model isn't just mapping pixels to motor commands anymore. It is building a continuous, predictive, latent world model.
It's essentially hallucinating the immediate future so it doesn't make a catastrophic mistake in the present. This all sounds incredible in simulation. But how did this pipeline perform when deployed on actual physical hardware?
The real-world evaluations were extensive. They tested on the GM100 bimanual manipulation benchmark, which evaluates fine-grained tasks like sorting blocks by color, scooping rice, replacing a paper roll, and packing fragile eggs.
Delicate stuff.
Very. And they also ran long-horizon mobile manipulation tests on two vastly different platforms, the Astrobot S1 and the Cobot Magic ARX X5.
Right. The Astrobot was navigating a room to sort objects into a fridge, and the Cobot Magic was wiping down a stove and moving pots around.
Yeah.
And from what I read, Lingbot VLA 2.0 demonstrated massive cross-embodiment transfer capabilities, succeeding even in out-of-distribution environments with novel objects that it never trained on.
It did really well.
But, and this is a big but, the researchers highlighted a very specific persisting failure mode. They documented a massive gap between the model's progress scores and its overall success rates.
Right. So the progress score measures how many sequential steps of a task the model completes. The success rate only triggers if the entire task is finished flawlessly.
Ah, I see.
The model frequently completes 90% of the steps with perfect precision. It navigates across the room, identifies the fridge, grasps the target object securely, and maneuvers its arm into the perfect position.
Okay, so what goes wrong?
It fails on the very final release or placement of the object.
The infamous last millimeter problem?
Yeah, exactly.
It's like an Olympic gymnast executing a flawless midair routine, but consistently stumbling on the dismount. Why is that final fraction of a second so universally difficult for AI to master?
Because that final placement requires sub-millimeter tactile and geometric feedback that generalized vision just struggles to capture.
Oh, because it can't feel it.
Right. When a robot is releasing a fragile object onto a shelf, the exact friction coefficient of its specific gripper pads and the micro-occlusions where the gripper itself blocks the camera's view of the contact point become the dominant variables.
You literally can't see the problem.
Exactly. The paper makes it clear that embodiment-specific kinematics, like the exact mechanical slop in a specific robot's wrist joints, combined with slight variations in camera viewpoints, are hurdles that broad visual representations haven't fully solved yet.
We still need a real breakthrough in tactile integration to solve that last millimeter.
Definitely.
But stepping back, the engineering lead here is just staggering. I mean, they took massive chaotic data from dozens of different robots and humans, mathematically sanitized it, wrestled it into a 55-dimensional control vector, and processed it with a collaborative MOE architecture that literally predicts the future geometry and causality of the scene.
Yeah, it's a huge step.
It really takes VLA models out of the run of lab curiosities
Yeah.
and pushes them toward viable industrial tools.
It shifts the entire paradigm. And honestly, it leaves us with a fascinating engineering thought experiment.
No.
Yeah, if this pipeline can successfully map humans, quadrupeds, bimanual arms, and mobile bases into a single 55-dimensional vector, what happens when we introduce entirely non-anthropomorphic hardware?
Like what?
Imagine trying to apply this exact framework to a swarm of microdrones, or like a factory floor comprised of 100 decentralized, cooperative robotic limbs acting as a single neural entity.
Wow, that's wild.
Right. Does this 55D space scale to alien embodiments, or will the next generation of physical AI require a fundamentally new mathematical topology for action representation?
That is the exact kind of problem that keeps ML engineers awake at night.
Oh, yeah.
Can a single transformer learn to pilot a drone swarm just by padding a few extra dimensions? Or does the unified theory of movement just break down completely?
Something to think about.
Definitely some things for you to chew on while you were writing your next training script. Keep experimenting, keep building, and we'll see you next time on AI Paper Slop.